Hello everyone, welcome back. So this is another data analysis video. Still working in Jupyter Notebook and using the different software libraries in Python. So in the previous video, the prior video to this one, I was demonstrating how to perform t-tests. So inferential statistical tests comparing two groups or two conditions. And in the previous video, I kind of demonstrated how to run a one sample t-test. So comparing a sample from a group on some score against some hypothesized population mean to see if it significantly differs, see if the group significantly differs from scores in the population. And I used the scipy .stats library to do that. And I generated some fake data, some random data about voting ages. So some of the data related to working out a load of random samples to work out the mean age of voters in the population as a whole, and another one, a sample looking at the mean age of voters in the county of Yorkshire. And what we found was there was at the 95% confidence level, at the 0.05 level of criterion level for statistical significance, we found a significant difference between the mean voter age in Yorkshire compared to the rest of the population. As I said, this is made up data, but it demonstrated that voters were significantly younger in Yorkshire than the population as a whole. Anyway, what I'm going to do this time is something similar, but I'm going to actually do a two sample t-test. I think hopefully if you've seen the previous video, you'll heard me say I can't think of many occasions where it's that useful to conduct a one sample t-test. It's often going to be the case you don't know what the population mean is, which is one of the arguments you have to put into the scipy t-test underscore one sample method. But in this case, we did know the population mean because we generated the data ourselves. So what I'm going to do in this video is demonstrate a two sample t-test, and in particular I'm going to use the independent groups t-test or the independent samples t-test. So this is comparing scores between two groups, two samples that contain different individuals, different observations, different participants. Okay, so it's not scores from the same people that are taken at different times. That would be like a repeated measures or paired samples design. I'll cover that in the next video. In this one, what we're going to do is run an independent groups t-test using scipy, the stats library from scipy. Okay, so to do this, we already have one sample group we're going to use, which was that mean age of voters in Yorkshire, and what I'm going to do is generate a second group to compare it against for mean voter ages, and this time I'm going to create a second set of dummy sample data relating to voter ages in the county of Hertfordshire. So what we're going to do is look to see if the age of voters is significantly different between Yorkshire and Hertfordshire, the mean age of voters. So if I run this cell here, I'm using, again, I'm not going to say too much about it, but I'm using the .rvs, the stats.random variables method to generate random data for sample size of 50, and I'm using a Poisson distribution. I explained in the last video why I was doing that. It's a discrete distribution. It measures occurrence of events over a series of time, and it's possibly a good distribution if we're looking at voter age, because you will get mortality and a decline in events at higher values or the longer you wait. Okay, so what you can see here is from running that cell, our mean voter age for Hertfordshire is 42.8. So if I scroll back up quickly, we can see from the previous video, the mean voter age for Yorkshire was 39.26, sorry, and the mean age for voters in the population was 43. So mean age for Yorkshire is again lower than the comparison sample, this is the Hearts Ages group. So Hertfordshire has a higher mean age for voters. But the question we're asking is that a significant, is it a statistically significant difference? So given the size of our sample, the degrees of freedom we've got, we're going to conduct an independent groups t-test to see if, although the mean of our sample for Hertfordshire is higher than the mean for Yorkshire, is it statistically significantly different? So to run an independent groups t-test in scipy, we're going to use the t-test underscore ind, so for independent method, and you can see the syntax for it there. I've already imported scipy, the stats library, and saved it, giving it the nickname stats. I'm calling stats.t-test underscore ind, and then in parentheses there are a number of arguments I've got to pass to this particular method or function. So A is going to be the first group, B is going to be the second sample group, and the third argument I'm specifying equal variances equal variances. I'm setting that to false. So the equal variance argument allows us to specify whether the samples meet the assumption of equal variances, so equality of error variances. And if we set that to true, it would assume they do. But if we set it to false, it will give us a more robust estimate. It'll conduct a more robust test of significance. Okay, so you can see here what I've done is I've specified group A that we're comparing is the Yorkshire ages, group B that we're comparing is the data for the Hearts ages that we generated and saved as an object Hearts underscore ages there. And if I run this cell, what you see is as we got here when we ran the one sample t-test, we get a test statistic and a p-value. So we've got t-test underscored ind, so independent t-test result, and in brackets it's given as the t-statistic, which is negative 1.708 if we round that to 3, and a p-value equal to 0.09. So at the kind of significance less than or equal to 0.05 level, this is not a statistically significant result in this case. So although the two mean group ages differ, and Hearts is higher than Yorkshire, that's not statistically significantly different. Okay, so that is using this particular test on generated data. So what I'll do just to finish this video is I'll kind of do a similar sort of thing. I run an independent groups t-test on an imported or existing data set. So what I'm going to do is, and you will probably have seen me do this in any of the earlier videos that I've created about cleaning and importing data. I'm going to import a data set that's saved on my laptop, and it's saved under the name weight height igttest.csv, so it's saved as a comma separated values file. And I'm going to import it and give it the name w_h_data, so weight height data. I'm going to save it as a data frame object, and I'm going to use the pandas p.read_csv method to import it and then just print out the head. So this is data that I kind of made up, I created myself, I believe. So looking at that, and I did it, I kind of simulated it in order to use it so my students could practice running t-tests and interpreting the results. So if I look at this, what we've got here is weight and height, age of participant, and we've got a categorical variable sex, 0 and 1. I believe 0 is the dummy code for males, 1 is the dummy code for females. So what we're going to do is, if we look at the data types on this next cell, we can see that sex is saved as an integer. So it's a category. We could put labels on it, and I've shown in other videos how to create sort of categorical labels and save categorical variables as kind of strings or objects. In this case, we can just leave it as that. It can be useful to add labels because it then makes it easier to interpret the output. But in this case, I know that 0 is male and 1 is female. So what I will do is run this, run the stats in independent groups t-test. and save it as a separate data frame object called res for results. So I'm basically creating this output data frame object, so data object, and that is equal to stats.ttest underscore ind, and within parentheses I'm passing the data that we want to use. And what I'm going to do first is compare weight, compare the different sexes, male and female, in terms of their weight, okay, to see if there's a significant difference between males and females in their weight, in their mean weight, essentially. And to do that, because these variables are sort of, they're not separate objects as they were in the previous example, where we've already worked out the mean, what I'm going to do is I'm going to pass the data frame object whdata, and then in square brackets I'm passing again whdata, and I'm specifying which variable to use, .sex, and then the double equals sign equals 0. So what this here is saying is take the sex variable from the whdata pandas data frame object, and use the participants, the observations that are set exactly equal to 0, which we know is male. And then after the brackets I've put dot weight, and what that is doing is it's basically telling Python to extract weights for males as the first argument for t-test equals ind. Notice in the previous call, when I ran it in the previous example, I kind of say a equals, and then the first variable, and then b equals, and then the second group that we were comparing, but I haven't actually done that here. I've just passed the two groups. And the second one here, you can see I've done the same sort of thing, whdata in brackets whdata.sex exactly equal to 1, double equals 1 dot weight. So basically what we're doing here is we're taking from the data frame the weight scores for males as our first group, from the data frame the weight scores for females as our second group, and we're going to use that equal variances equals false. So we're going to ask for a more robust t-test. So if I run that, you don't get any output because I haven't actually called the res object. So if I do that in this next line, I could have included it in the same cell, but sometimes I just like to mix things up. So you know, it kind of highlights the fact that, you know, if you run this and don't get anything, it doesn't mean it hasn't worked. And what we see here is for our independent groups t-test, we've got a test statistic, a t-value of 5.35. P-value is equal to negative, sorry, it's going to be 0.005, something like that. So it's less than 0.001. So what we're seeing here is 5.66 to the negative 10 times 10 to the negative 6, something like that. So this is scientific notation, and it basically tells us it's a really small number. What it's telling us to do is kind of move this decimal in the negative direction 6 places, essentially, to make it smaller, to make the value smaller. So much less than 0.001. So a statistically significant result. Okay, so there is a significant difference between mean weight for males and females. We haven't actually looked to see what the mean weight of males and females is yet, but like before we do that, let us extract some other information that would be useful, such as the 95% confidence intervals for our t-test. And what we're going to ask for here is 95% confidence intervals around the group mean for male weight. So if you look here, what I'm doing, I demonstrated in the previous video where I ran a one sample t-test, but it's exactly the same really. I'm creating a standard error, I'm calling it sigma really. I'm taking the male weight, standard deviation, dividing it by the square root of the sample size, and then I'm going to use this stats.t.interval for confidence interval. I'm setting it at the 0.95 level, so that gives us 95% confidence intervals. Specify the degrees of freedom. The location argument is going to be the mean weight the mean weight is the kind of the center that is going to be. So is the mean weight for males in our data, in our weight height data set, and it's going to give us the 95% confidence intervals around male mean weight. Okay, and I've passed the scale equals sigma, so I've passed the standard error we calculated there. And what we can see is, so the confidence intervals are around 95% confidence intervals are between 73 and 80. So this could be kilos or something like kilograms, something like that. So male weight is, 95% confidence intervals are between 73.63 and 80.20. So because we've got this highly significant, statistically significant result, what that's telling us is when we actually look at the mean weight for males and females, it's the mean weight for females is going to be different. It's going to be outside of these 95% confidence intervals. So from what I remember, it's much lower. So there you can see if I run the next cell, which is just, all I'm doing is printing out mean weight. And you can see the mean weight for males is like 76.91, which sits kind of in the middle, roughly, of this 95% confidence interval. And the mean weight for females is 61.64, so much lower than this kind of lower bound. So hence the reason we got a statistically significant result. Okay, I'm going to run just one more using the same data, but this the same analysis essentially, but this time we'll just see if there's a difference between the sexes in terms of height in this data. So I'm saving it as a data frame object called results2, res_2, and we're calling the stats.t_test_ind, so independent groups. And this time I'm passing exactly the same data from the data frame, but I'm using .height. So I'm telling it to extract all the males, height for all the males, and the second group is, just messed up the data. Let me sort that out. Somehow managed to copy and paste my data into the wrong place there, and I'm passing the second group is the height scores for females. Again, we'll ask for a robust test by setting the equal variances to false. And if I run that and also get the output for the results in the second cell, we see again we've got quite a similar t statistic to the one above. So what we're seeing is we've got a t-value of 5.62 if we round it to two places, and again a p-value of much less than 0.001. So if we move this decimal kind of 6 places to the left, that would be 0.00006, 0.00015, that type of thing. All right, so highly significant difference between males and females in terms of their height as well as their weight. Same thing as before, I'm going to just create the confidence intervals, and we can see, so I've asked for the confidence intervals for males, male height, the mean is the location. So we've got male height, 95% confidence intervals around the mean are between 173 and 177. And if we print out the heights for males and females, what you can see is female height, the mean is about 164.64. So it's again much lower than it falls outside the 95% confidence intervals. Hence the reason we got this statistically significant result on height. So hopefully that's useful. That's kind of that's just some of the kind of stats you'd probably want to extract and report when you're reporting the results of an independent group's t-test. So in the next video I'll kind of do something similar, but I'll run paired samples t-tests on simulated data and then also on a real data set.